Topic Notes 2.3 pH and the carbonate cycle. This image is of a pillar coral out in the Florida Keys, and it's a really representative organism for the importance of pH in the ocean. Now, hopefully you've learned about pH in the past. We're going to do a brief overview of it here, and then move on to talk about how it works in the ocean environment. So, let's get going. So here are your main ideas. First, the ocean has a pH of about 8 and is maintained by the process of buffering. Also, increased atmospheric CO2 is resulting in decreased pH within the ocean, which is called ocean acidification, causing negative impacts on marine life. But today we're going to try and focus on pH, understanding that pH is a scale that represents the balance between positive hydrogen ions and negative hydroxide ions in liquid, describing the pH of seawater and explaining the concept of buffering in terms of carbon dioxide, which is really important, and of course discussing the concept of ocean acidification and its impact on marine life. Now, pH is something you've probably heard about in many science classes in the past. In fact, you probably did a lab somewhere along the way with the little paper wheel that you see in the bottom left. It's called a litmus paper, and you would put drops of whatever liquid on that, and it would turn colors and tell you what the pH was. For today, I'm just going to do a brief overview of pH, hoping that it'll trigger some memories. First of all, chemicals in general, chemical compounds that is, are classified as either acids or bases depending on how they ionize water. So, an acid releases hydrogen ions when added to water. A base or bases are alkaline substances, and they bind hydrogen ions and remove them from the solution. Now, some simple acids that you would know of, for example, there's some lemons in that middle picture. Those are examples of acids, but then we also have bases, Arm & Hammer baking soda, for example, things like that. So pH is simply an indicator of the concentration of these hydrogen ions in a volume of solution. Now, so what is pH? Well, the actual term pH is kind of difficult to really pinpoint in terms of why we call it that. But today we tend to refer to it as the power of hydrogen, just to give you an idea of what we're talking about, hydrogen ions. Now, I do have to have a bit of an advisory warning. When we talk about hydrogen ions, H+, what we're really talking about is hydronium ions, which are H3O+, but there is a long-standing tradition is to simplify this as just a hydrogen ion, H+. And in terms of the breadth and depth of this course, the simplification will work just fine, but if you do go on to study more in depth in chemistry, keep that in mind. Either way, pH represents the negative log of the concentration of hydrogen ions. And the scale goes from 0 to 14, with 7 being the neutral point. Anything below 7 has a high acidity, and anything above 7 is more of a base. Now that means the concentration of hydrogen ions is higher at the lower numbers of the pH scale and lower at the higher number of the pH scales. It's kind of inverse. So this is a logarithmic scale, which means that any change of any one pH unit indicates a tenfold change in the concentration of hydrogen ions. Now, water, as we've learned already, is pretty incredible. Well, H2O, water, can act as an acid or a base, releasing or accepting hydrogen ions. Pure water, like we mentioned before, has a pH of about 7, so it's got about equal concentration of hydrogen ions and hydroxide ions. If you draw this out, H2O dissociates into hydrogen ions and hydroxide ions. Again, that disclaimer, this is a simplification, but it represents pretty well what we're talking about. Now about the ocean. Ocean water is slightly alkaline. Its average pH is about 8. Now, this happens because it contains alkaline ions, including bicarbonate and carbonate. These ions bind hydrogen ions and remove them from solution, thus making the pH higher, increasing it, and thus decreasing the concentration of hydrogen ions. Interestingly enough, the pH of the ocean is relatively stable due to something we call buffering. A buffer is a substance that reduces the tendency of a solution to become too acidic or alkaline. It basically keeps it in a narrow range. And in the ocean, this is really important. In fact, in the ocean, carbon dioxide combines with water in several reactions, which we're going to get to in just a few minutes, that will either free up or release hydrogen ions. Now we're going to look at the entire process as a whole. First, you have carbon dioxide in the atmosphere. Now that carbon dioxide as a gas will diffuse into the ocean, and it will combine with water molecules to create something called carbonic acid. Now this is actually a weak acid found in carbonated drinks. Now some of the carbonic acid molecules dissociate into a bicarbonate ion and thus release a hydrogen ion. Now remember, that's sort of the definition of an acid when it releases hydrogen ions and thus decreases the pH. Bicarbonate ions can further dissociate into carbonate, thus releasing an additional hydrogen ion. It's also important to note here that the carbonate, being a -2 ion, can actually attract calcium, which is a +2 ion, thus making calcium carbonate. This will come up a little later when we talk about ocean acidification, but for now, there is a dynamic equilibrium between the carbon dioxide, the bicarbonate, and the carbonic acid. This process allows ocean water to maintain or buffer its pH at around 8. Now, just to reflect on that, here are some simplified bullets to explain what we just talked about. Now, pH can change in a variety of ways in the ocean. We're just going to talk about this one first, and this is through depth. Okay. Now, pH varies with depth based on the availability of CO2. In the surface waters, where it's shallow and there's a lot of sunlight, you have a lot of photosynthesis. So even though you have a lot of animals going through cellular respiration and producing CO2, you also have a lot of photosynthesis taking it back up again. So that means your pH tends to be a little higher in the surface waters, closer to 8.5. Now, as you start to go deeper, what you'll end up having is a loss of photosynthesis, or at least a reduction of it, so that there's more respiration going on. This means there's more CO2 available, and it will start to drop the pH, and it'll, go down around 7, 7.5. Now, below 3,000 meters in the really deep water, you tend to get a little bit more above 7.5, and that's because there's less organic activity. There's less respiration going on anyway, even if you don't have photosynthesis going on. So it'll kind of buffer up a little bit at that point. Now let's get into ocean acidification. Since the Industrial Revolution in the 1800s, human activity has really caused a significant increase in atmospheric CO2. As you can see in this graph, back in the 1960s when we started measuring things, it was not above around 320 parts per million. Now we are looking at it way over 400 parts per million. Now this increase in concentration is going to be reflected in the ocean because, of course, CO2 is soluble in water and is going to diffuse into the ocean. If you reflect back on that carbonate cycle we just learned about, you can see where some of the issues might arise. Ocean acidification is sort of the canary in the coal mine. Over the years, the ocean has actually absorbed about 1/4 of the CO2 humans have released into the atmosphere. That basically means the more CO2 we've put out into the atmosphere, the more the ocean has been sucking it up. This increased CO2 level in the ocean is causing an imbalance. In fact, we're actually documenting oceans becoming more acidic. This is a big problem if you happen to be an organism that uses calcium carbonate as a shell or a part of your skeletal system, whatever. In fact, you can see in these images below this shell that's been exposed to a lower pH over a period of 45 days. It starts to dissolve. So you can imagine this being a big issue. Any organism, basically calcifying species of marine life, corals, crabs, oysters, even plankton, which are the base of the food chain, are at risk from ocean acidification. And it is directly tied to the amount of carbon dioxide we put in the atmosphere globally. This can cause a disruption in food chains. It can also cause economic and food production issues for people, and not to mention just a mass die-off of marine life. This is a picture showing sort of a before and after of a elkhorn coral. Of course, it's not the exact coral, but these are the things that are actually starting to occur. Corals build a calcium carbonate skeleton. They build reefs this way. And as the pH becomes lower, more acidic, they are not being able to calcify well, and that's causing them to have problems and even die off. Now, we are still learning about the relationship between carbon dioxide in the atmosphere into the ocean, how it's sequestered. Ocean acidification now is becoming a part of that story, and it will continue to develop over the next coming years and decades. Either way, it is concerning marine scientists greatly because we're seeing some serious potential problems through these processes. So now I'm going to turn it over to you. How do you think ocean acidification is going to impact the economy of, let's say, our local Florida Keys, which obviously have access to one of the largest coral reefs in the world? Make sure you respond on your note summary sheets, and until next time, keep thinking.